start with principle of maximum entropy, right? So that is, so anyway, again, these are all things that you should understand very deeply, and you should also be able to write all of the expressions that I write without looking at the notes. And if you, I think you'll be able to do it. Okay? So principle of maximum entropy. Right, this is kind of the basis for a bunch of things. So all it says is, you know, you should always, if you're trying to set a probability distribution, you should always maximize entropy of that probability distribution subject to any information you have at hand. Okay, so it's really maximize P minus expectation over P log P subject to information constraints. Well, I'll tell you what those constraints are, right? So one constraint could be, for instance, P is a probability distribution, right? That means when you integrate P over your range, you get 1, and P is positive, okay? So that's a constraint, okay? Example of constraints is integral P of x dx equal to 1, P of x greater than or equal to 0, right? So these are natural constraints, okay? But typically that's by itself is not, it is probably enough if you know the range, okay? So let's say your range of your x varies between A and B, right? 1D interval. So the solution to this optimization problem with these constraints is just P of x is 1 over B minus A, okay? For this particular example, right? If you know nothing about a probability distribution other than the fact that it is a probability density in this case, and it varies between, say, B and A, then the solution to this maximum entropy problem is just P of x is 1 minus B minus A, the uniform distribution, okay? So that should be straightforward, okay? If the information constraints were, okay, again, so that was one example. Now, if the information, again, you have the same, you go to some other problem. Let's say the projectile example that we considered, okay? The only thing you know about the errors is you know the mean is 0 and your standard deviation is sigma, okay? So let's say that's the only thing you know about the errors because that is the only thing that the experimentalist told you, okay? So we want to maximize entropy subject to integral minus infinity to infinity, P of x dx equal to 1, and of course P of x, let's say P greater than 0, and expectation of P equal to, should say expectation of E, that sounds super weird. Expectation of x is mu, and the expectation of x squared is mu squared plus sigma squared, okay? In this scenario, the maximum entropy distribution would be the Gaussian distribution, okay? So P of x equal to 1 over B minus A is the solution to this optimization problem, and P of x equal to 1 over square root of 2 pi sigma squared. So this is the solution to this optimization problem, okay? So the principle is very simple. I mean, it is somewhat conservative, right? That's why it's a principle. And it says, you know, don't bias your probability distribution by things that you don't know. Okay, so just keep everything as conservative as possible. And then when new data comes in, you'll be in the best position to, update your probability distribution, right? And being unbiased in this sense, I think intuitively is okay, right? So this is a fundamental principle, which is the starting point for many things, right? And it makes a lot of sense. If you impose more constraints, you'll get obviously different distributions. In fact, you can bring physics in here. You bring physics into this, and you bring dynamics into this, you could get something like, the Boltzmann distribution, for instance, Gibbs distribution. So anyway, so this is fundamental. So this is the logical starting point for how you set a probability distribution, okay? So here there is no data, right? This is before you have data. All you know is something about the underlying probability distribution. Okay, your data has not entered the problem, and then you have these information constraints. Any quick questions here? Right, this is the first thing, right? So this you should know. I mean, you should be able to write at 3 a.m., right? Okay. Yeah.
Is this what your P0 is supposed to be in your principle of
P0 is whatever it is. Max P minus, basically, maximize entropy subject to whatever constraints, whatever information constraints you have.
Yeah, so this is P0.
Yeah, I mean, if this is the only information that you know, yeah, then that would be the correct P0 under this principle. If this is the only information you know, you only know the range, that would be a P0, right? So the focus is on maximizing entropy subject to any information you have about your problem. Okay? Crystal clear? All right. So that's the first thing. Now it's 3:05 a.m. You have some data, okay? So now you have, let's call this as P0. I mean, it's probably a good idea to do that, okay? So let's call the solution to this optimization problem as P0, okay? But now you have some data coming in, so you basically want to update your probability distribution, okay? So this is principle of maximum entropy, and then you can, if you have data, you can say principle of minimum information. And what is the principle of minimum information? Very similar. So you have some probability distribution P0, right? That encodes all of your beliefs and all of the information you have on a certain problem. Okay. And now some data comes in about that problem. How should I update my probability distribution? Let's call this updated probability distribution as Q. Okay. So the principle of minimum information says, if you have, you're minimizing this over Q. You want to minimize the deviation of your new distribution from the old distribution, subject to constraints. I'll call it data constraints. Okay? And yeah, maybe this was information constraints, and this is data constraints. So this is also very intuitive, right? You obviously want to not deviate too much. You only want to deviate the minimum amount from your beliefs, and then subject to data constraints. So it sounds intuitive, but what may not be intuitive is why the KL divergence? Why can't it be something else? Why can't it be some least squares, or why can't it be some deviation, right? In essence, the gist of it is you don't want to depart too much from P0. So you want some distance measure between your new distribution and your old distribution, in your posterior and your prior or your beliefs, whatever. Why KL divergence? Again, that's where, as I said, Shore and Johnson have a paper that shows the KL divergence is a great choice. And this particular minimum information principle is also a great choice because it agrees with a bunch of axioms, right? And again, axioms are not laws, axioms are just axioms. Okay? So, yeah, any questions here? Yeah.
And suppose we're not confident in our initial beliefs of our P0. Isn't that a very restrictive sort of optimization for us then?
If you're not very confident in your original P0, see, it's not, well, then the data would have, then you have to be more confident in the data, right?
Yeah.
If you're not very confident in your belief, you have to be more confident in the data. Mm-hmm. So those data constraints will hopefully help you there. Or even if the data constraint doesn't help you, you're still in a scenario where whatever amount of information that's coming to you or data that's coming to you, you're updating your beliefs consistent with that. There is no law or axiom that says every time you should be right, right? It's just the principle that, well, this is the best you can do under these constraints. Okay? Yeah.
So is it fair to say that maximum entropy gives you the shape of the distribution and minimum information gives you the parameters of the distribution?
No. Because in both cases, you're still optimizing over the shape. You're still, these are all functional minimizations, you're still minimizing or maximizing over the entire profile. But I think I see where your question is coming from. Generally, we use this to say that is my prior and that is my posterior, and posterior is generally with relation to your parameters. Yeah.
Would this, under some condition, collapse to just parameter estimation?
Yeah, sure. If data is coming in, this would be precisely parameter estimation. In fact, when I write down a very specific constraint, this is precisely Bayesian inference, right? So that's why this is more general than the Bayes rule, because the Bayes rule would be a special case of this, okay? Which is the next thing. If the specific constraints, again, remember, anytime you have a minimization problem subject to constraints, you can write it as a Lagrange. You can basically write the Lagrangian, okay? So minimum of Q dKL, difference between Q and P0, plus expectation over Q, minus log, okay. This is my probability of Y given. I used X before, so I'll use X here. So if the data constraint comes from the likelihood, right? Remember, whenever you're looking at the likelihood is nothing but, or at least it can be conceptualized as, given the model parameters, what is the likelihood of observing the given data, right? So this is a specific kind of data constraint, which is the likelihood type constraint. Basically makes the principle of minimum information to be this. Okay, this is a specific, again, this is general, and this is specific, okay? And turns out, okay, let's call this equation 1, let's call this equation 2. Turns out, infimum is probably better to say that. So solution to 2 is actually probability of y given x p naught divided by probability of y. Okay, which is nothing but the Bayes rule. Okay, so in this particular context, you can think of the principle of maximum entropy as a principle where you set your prior, right? It's more general than that, but in this particular case. And then the principle of minimum information is that a specific data constraint is this, and a solution to this problem is actually the Bayes rule. Okay? This is clear. We saw this, right? So again, so all of this you should be able to write without looking at anything, because it should be very intuitive, right? It's just the deviation from P naught in a particular measure, and then this is just the likelihood. You know what the likelihood is. And anyway, this is what it is. Yeah.
Why is there a negative sign? Isn't the likelihood?
It's a negative log likelihood. If you have a positive, remember in maximum likelihood estimation, we were maximizing that, right? The easy way to think about it is a Gaussian has a minus half in it.
You want a minimization.
Yeah. The Gaussian has a minus half in it, right? So that's the easy way to think about it. Okay, so very clear, right? So far, things should be straightforward. Maximum entropy and then principle of minimum information, and that is connected to Bayes rule, Bayesian inference. So all of this is very nice, except especially when you have high dimensions, this is extremely difficult to solve. This is also extremely difficult to compute, because you have to do effectively integration in a very high dimensional space. So it doesn't quite work out. So the last thing we did is variational inference. You know, I was not planning to review this, but I decided to review because depending on how much time we have at the end of the learning part, we'll come back to variational inference and do some things. So the idea of variational inference is also super intuitive. You're effectively trying to solve this problem. Okay? You're still trying to solve this particular problem, but it is very difficult to solve because of, especially in high dimensions and in many cases. So instead of Q, you're trying to find an approximation to Q. Okay? An approximate approach to equation 2, right? So instead of Q, we'll replace Q by, I'll just call it Q phi, and we'll try to solve for Q phi. So maybe we can get a little more specific here. Okay? So let's say the Q that I'm seeking is probability of theta given y. Okay, this is the Q that I'm seeking. I'm seeking variational inference is more general than this, but let's be more specific. I'm seeking a P of theta given y, which I can get from this rule, but that is expensive. So instead, I will work with P phi of theta given y, which is an approximation to the true P of theta given y. And so again, very natural. So I want to find P phi such that it gets as close to P of theta given y as possible. So this is my goal. Again, remember, when I say P phi of theta given y, it means I'm representing this unknown probability distribution in parametric form. An example of a parametric form is a neural network, and phi would be parameters of the neural network. So one y, yeah, anyways. So, or it could be, whatever your favorite functional form is, okay? So the cute trick in variational inference is you can show that, this is, first of all, you cannot solve this problem directly. Why can't you solve this problem directly?
You don't know either of those.
Yeah, exactly. You don't know this, and this is your goal is to compute this. If you knew that, then there is no, there is no reason to be doing this whole thing. But variational inference use a very cute trick to convert this problem to an equivalent minimization problem, which would go something like minimize expectation with respect to P phi of theta given y. Oh, actually, no. Let's first write the KL term first. So again, it should be very intuitive. PKL of P phi of theta given y, the deviation from P of theta, plus expectation over P phi minus log P of y given theta. I'll let you write down and we can explore it. It's a very neat, one of those very neat tricks that is very intuitive, works really well. Right, so you look at this. This is your prior, right? Which maybe you used maximum entropy principle or whatever it is. This is what you want. This is what you want to find, and then this is just the likelihood of the model. So you minimize this. Oh, yeah, there is this other benefit here. You're minimizing this over phi. You're minimizing this over a finite set of parameters instead of an infimum over some terrible function space. Okay, and so this problem is generally easier to solve, easier to operationalize, because most if you use something like PyTorch, the ability to compute gradients, ability to optimize, so all of that is built in for you. Okay. So that's really what we've been doing so far. right? Maximum entropy principle, minimum information principle, and variation inference, right? So again, it looks like we wrote down a bunch of math, but you should be able to write it down, right? Because if you know the definition of entropy and definition of KL divergence, what a prior is, what a likelihood is, then that's pretty much it. Okay, so can I expect you to write this in the exam? Be fair, right? Because I expect you to remember what the definition of entropy is, and I expect you to know what the probability distribution is, and yeah, then what each of these things mean. Okay, all right, that's really what I wanted to say.